So hi, welcome back to our channel. Again, I am Nesfi Joy Duran together with Mr. Arnel Kitani from School of Engineering and Technology. So last lecture we've done tackling about the mathematical modeling, the MATLAB fundamentals, the programming, the roundoff and truncation errors. So today we will be talking about the roots finding, which includes the bracketing method, the root open methods, and the optimization. So we have here the bracketing method. In this case, you have to identify where the root is and then identify some value of x above and below where the root is. And the bracketing method are essentially works by slowly adjusting those bounds and word until close it to where the root is. We may be know roughly that a root is not a value of 2. For example, we might choose the value of upper and lower limits of 1 and 3, and we want to ensure that those limits round a root. So to explain the bracketing method, we have here the subtopic, which is the bisection methods. Performing bisection methods, we have to prepare a plot of the function f of x. Next, choose an interval with bounds a and b, the bracket the desired root we're looking for. The root should appear the interval from a to b, and the bracketing method will only work if function of f sub a and function of b have different signs. As you can see in the illustration, it is illustrated the 5 steps in performing the bisection in finding the roots. So we have here the 4 illustrations which illustrated the 5 steps in finding the root using the bisection method. So the first illustration, we've done it explaining the first and the second steps. So we have now our bounds, which is the bound A and the bound B. And also we have our midpoint. And our bound A and bound B has a opposite sign. So we can now go to the third step. Our third step is to find the midpoint, which illustrated here. So we have C1 is equals to 1/2 times the bound A plus bound B. So it is simply to calculate the midpoint of the interval A and B. We can call that as C1 or C sub 1, where the first estimate for the root of the function f that lies between the points A and B. And the fourth step is to evaluate the function of x at a point C1 or C sub 1. We've done in our first estimate, which is the C1. And now we are ready to locate our second estimate. So in step 5, if function of A and function of C1 have opposite sign, it assumes that the root we're looking for lied on that interval. And otherwise, if function of A and function of C1 do not have the opposite sign, then the root must be the interval in C1 and B. So we will repeat the step 2, 3, and 4 using that interval instead. As stated in the bracketing method, so in finding the estimate or the roots, we must have a different sign or the opposite sign. Opposite sign in using our intervals. So we have our 2 interval, which is the function of A and function of C1, and the second interval is the function of C1 and the function of B. Follow the principle of bracketing method, we have to use the second interval, which has the opposite sign, and which is the function of C1 and the function of B. So function of C1 have a negative sign and function of B have a positive sign to know the second estimate, we have here the formula C2, which is the second, considered as the second estimate, is equals to 1/2 times the function of C1 and plus function of B. So we've done in locating our second estimate. So those process or those steps is repeatable in finding the second, third, or fourth estimate. Hence, in finding the root using the bisection, we must consider our interval that it must have the opposite sign. So next, we will be talking about the open methods. So open methods, of course, that we have no longer have the upper bound and the lower bound, but we give it a single guess and we find that solution on the finding of the roots. In open methods, we have also the subtopic or the two methods of performing open method in finding the roots. So first, we have the Newton-Raphson method, and second, we have the Secant method. These two methods are literally the same method, except that the Newton-Raphson method, we need analytical expression for our function and its derivative, whereas the second method is a fully numerical and we don't need analytical expression for any of those. So we have here the Newton-Raphson method. So we start off in something looks familiar, except that we have no longer bounds. So we have a function of x passes through 0 at some point and we want to figure out where the point is. First, what we will do is to make an initial guess as to where the root is. This is similar in the bracketing method when we choose our bound. And we need those bound to find where the root was. Here our guess just need to be near where the root might be. We call that guess x sub 1. The reason why we use that subscribe 1 is we will successively refine that in every iteration we will have, such as x sub 1, x sub 2, x sub 3, x sub 4, and so on. So we have now our guess x sub 1, and what we will do is to evaluate the function at x sub 1. So at this point, we have analytical expression for the function, and we know that the function value at the point we can come up with the equation for a line that passes through that point, and we make slope for that line the same as the slope of the function at the point we just evaluated. We go to our equation of the line and we use a slope and a point. In this case, our point are x sub 1 and y sub 1. So instead of y, we just have our function. So we really have our function, the function of y, which is function of x, and the function of y sub 1, which is the function of x sub 1. So instead of, we have a derivative of f, which is the slope, so we have just have the x sub 1 times x minus x sub 1. So we're using f instead of y. So we have our equation for the line, and to find out where the line is passes through 0, we set that value where y was, or f of x. We set that 0, and so for x sub 2, this will be our next guess as to where root will be. So we will solve this equation for x sub 2 and we will end up here. What we see is our new guess, which is the x sub 2. The old guess minus the function divided by the derivative evaluated at the point x sub 1. So x sub 2 tells us where the line crosses x-axis, and it's our next guess where the root might be. As you can see, we already have our second guess. So to solve or evaluate the next guess, we just have to repeat the steps we do in evaluating the second guess. So now we've done explaining open methods using the Newton-Raphson methods. So next, we will be talking about the optimization.
Optimization, in the most general sense, Optimization is the process of the creating something that is effective as possible.
As engineers, we must continuously design devices and products that perform tasks in an efficient fashion for the least cost. Thus, engineers are always confronting optimization problems that attempt to balance performance and limitations. Also, from mathematical perspective, optimization deals with finding the maxima and minima of a function that depends on one or more variables. The goal is to determine the values of a variables that yield maxima or minima for the function. This is also similar to the root finding that we tackle in chapter 5 and 6, that is both involve guessing and searching for a point of a function. Thus, the difference is that the root finding involves searching for the location where function equals to 0. In contrast, optimization involves searching for the function extreme point. To explain further, we have here the definition. So, optimization is referred to the process of finding the maximum or the minimum of something as optimization. The maximum or minimum values themselves are sometimes called extrema. So we have here the application that proves how optimizations that important. Here, it maximizes production of a company, minimize expenditures of the company, minimize energy expended by an organism in foraging, find time at which drug concentration in a patient peaks, determine the peak number of people sick during an epidemic, and lastly, determine chemical parameters producing the fastest reaction. As you can see in the illustration, we have the two types of extrema, which is the local max or minimum and the global max or minimum. So local maximum or minimum is the highest or lowest point in an immediate neighborhood. So the global max and minimum, highest lowest point in the world, possibly an infinite or finite domain. So yeah, we've done explaining the roots finding, which includes the bracketing methods, the open methods, and the optimizations. So thank you for watching. Once again, this is Nesfijoy Duran together with Mr. Arnel Kitani from School of Engineering and Technology.